My today's topic is based on two important uh, things. One is called multinomial distribution, and another is called multivariate distribution. Now, multinomial distribution was actually part of your module 1 of the syllabus, and multivariate is part of your module 2 of the syllabus. But multivariate, this particular word hasn't been written in the syllabus. Instead, bivariate, the term bivariate was written. Now, I intentionally skipped multinomial in module 1 is because I wanted to show the two different entities under the same umbrella, because although the names look very similar, multinomial and multivariate, their meaning is very much different from one another. So what multinomial actually represents, multivariate doesn't represent that thing. So if I taught you this multinomial distribution in module 1, you might have forgotten this till I reached module 3. So I wanted to show you the two things simultaneously. Therefore, I skipped multinomial distribution in the first module. Okay, so we can consider multinomial distribution to be the part of first module, but yet I have decided to go with this process. Okay, so my first question is about what is the difference between multinomial and multivariate distribution. What is the difference? Let me understand the difference first of all. The difference is, number one of the important conditions of binomial distribution is that the experiment under consideration has two outcomes. If we talk about binomial distribution, we already know that we always talk about success and failure. So outcomes can be categorized in two different ways. And not only this, each outcome has its own probability. Okay, now what is the formula for binomial distribution? NCX p to the power x q to the power n minus x. Now, if you think carefully that NCX p to the power x q to the power n minus x, this particular thing can be obtained in some other way. How? If we expand by binomial theorem, the expression p plus q whole thing to the power n. If I expand by binomial expression, by binomial theorem, the expansion of p plus q whole thing to the power n, the nth term will be like this: ncx p to the power x q to the power n minus x. Okay, what do I say? I say if I expand this quantity p plus q whole thing to the power n, then its nth term will be ncx p to the power x and q to the power n minus x. But since there are only two parameters, not parameter, I must not say parameter, there are only two terms in this expansion. Okay, two terms are in the expansion, one is p and another is q. So therefore this is called binomial. Okay, now in multinomial distribution, what happens is that we consider not only two outcomes of the experiment, we consider all possible outcomes of the experiment, and the number of outcomes present in the experiment is more than two. If the number of outcomes present in the experiment is more than 2, then if we expand it, then such distribution, such probability distribution is called multinomial distribution. Okay, so multinomial distribution is some kind of generalization to binomial distribution. But multivariate distribution is something else. What is multivariate distribution? Multivariate distribution talks about that kind of distribution where the number of random variables is more than 1. That is called multivariate distribution. Now, let us see what is written over here. So one of the important conditions of binomial distribution is that the experiment under consideration has two outcomes. But if in an experiment there are more than two outcomes, the probability distribution is multinomial. When in an experiment there are more than one random variables, then the distribution associated with the pair of random variables is called multivariate distributions. I must, you can say the pair of random variables, or you can say pair means this, I'm not talking about the ordered pair only. I'm talking about the, I can talk about the triplets or quadruples or n tuples also. So if there are n variables, n random variables in a system, then we can consider all the random variables in parenthesis, and we can write capital X1 comma capital X2 comma dot 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 capital Xn. So if more than one random variable is associated, then it is called multivariate. In binomial problem, in binomial theorem, only one random variable was present. So that was univariate distribution, not multivariate. So binomial distribution is a univariate distribution, and it's called binomial, but a particular distribution where number of outcomes is more than one, more than two, then it is called multinomial. And if the number of random variables associated with the system is more than one, it is called multivariate. So this is the difference between multinomial and multivariate distribution. Okay. Now, let me talk about the proper definition of multinomial distribution first of all. If capital X1, capital X2, capital Xn have multinomial distribution, I am considering here multivariate case also. Multivariate and multinomial has been conjoined together. So if there are small n number of random variables, so they will be having some different values like x1, x2, xk. Okay, you can consider here is a printing mistake. You can consider k here, x1, x2, xk. So therefore these values will be small x1, small x2, and small xk. So if the probability density function of this can be expressed as probability of x1 comma x2 comma dot 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 xk, these are all possible outcomes of the experiment, and theta 1, theta 2, theta k, these are the probabilities of each of these outcomes. X1 is appearing with probability theta 1, x2 is appearing with probability theta 2, xk is appearing with probability theta k. Then this probability density or probability mass function, not density, mass function, can be written in the following way. N, this is not NCX. Although I have written this notation like this, I cannot read this notation because it cannot be read. So you just see, in the parentheses on the topmost part I have written n, in the bottom part I have written x1 comma x2 comma dot 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 xn. This expression means I am actually trying to write n factorial by x1 factorial x2 factorial into xk factorial. This expression has been denoted by this calculation has been denoted by this notation. Okay, multiplied by each probability raised to the power x1, theta 1 raised to the power x1, theta 2 raised to the power x2, theta k raised to the power xk. Remember, theta 1, theta 2, theta k are the probabilities. X1, x2, xk are not probabilities. These are the values of the individual random variables. So if the probability distribution is like this, then we call them multinomial distribution. Let me solve a very simple problem. The problem is, suppose a certain city has three newspapers, capital A, B, and C. Okay, newspaper A has 50% of the readers in the city, newspaper B has 30% readers, and newspaper C has remaining 20%. Find probability that among 8 randomly chosen readers in the city, 5 will read newspaper A, 2 will read newspaper B, and 1 will read newspaper C. And we will assume, for the sake of the problem, that none of them reads more than one newspaper. Otherwise the thing will become a little bit complicated. Okay, we have to consider all the cases, okay, with union sign in between. Now if this is the scenario, then we can extract out the values which are given for different variables, which has been shown in the formula of probability mass function above. So you see, since there are three newspapers, so we'll consider three variables, x1, x2, x3, and since 5% reads newspaper A, so x1 will be having value 5, 2 persons read newspaper B, so x2 will be 2, and 1 person read newspaper C, so x3 will be 1. So actually there are the random variables capital X1, capital X2, and capital X3. These random variables are having represent the number of persons reading a kind of newspaper. Okay. Now the random variable capital X1, which is associated with newspaper A, is having the value 5. Random variable X2, which is associated with newspaper B, is having the value 2. And random variable C, which is random variable X3, which is associated with the newspaper 3, is taking the value 1. And since 50% of the readers read newspaper A, so X1 has got probability 0.50, and X2 has got probability 0.30, and X3 has got probability 0.20. So I have expressed each and every item with respect to the above notation. Just correlate these two. Now I am going to calculate the quantity, this n factorial by this. What is n here? N is 8. 8 randomly chosen readers. 8 readers have been chosen random way. So here the n is 8. Number of experiment is 8. And in the below I am writing 5 factorial, 2 factorial, and 1 factorial by the formula. And all the probabilities have been raised to the corresponding power of the variables. Like since 5 has got a probability 0.50, 0.50 has been raised to the power 5. Since 2 has got probability 0.30, 0.30 has been squared. And since 1 has got probability 0.20, 0.20 is raised to the power 1. So you just correlate this yellow marked formula with this gray marked calculation, and you will understand. And thus we can calculate the probability as 0.0945. So thus we can calculate the probability corresponding to a multinomial distribution. So what we have done here is the calculation of multinomial distribution. Okay, now I am going to get into the details of our topic of module 3, the first topic of module 3, which is nothing but bivariate distribution. Now what is bi? The word bi means 2. Okay, so the word uni means 1, multi means more than 2. Okay, so in this case I shall not talk about the general multivariate cases. I will only consider the bivariate cases as has been mentioned in the syllabus. So let us start discussing about that. So my next topic is about bivariate distribution. Okay, I have pasted this particular definition from the book of John Fund. Okay, this saved much of my time. Okay, so I have just because since you are reading, I hope you are reading your. I am referring the book to you, the John Fund Mathematical Statistics. So it should be better. It would be better if you learn the definitions from the book itself. So I have pasted. I have not typed in. I have pasted the definition as it is. So what is the bivariate definition? Bivariate distribution. If capital X and capital Y are discrete random variables, we write the probability that capital X will take on the value small x and capital Y will take on the value small y. Simultaneously, capital X and capital Y are taking two different values, small x and small y. And we are considering the joint probability. This probability is called the joint probability. Both the probabilities are considered simultaneously, not separately. In the previous case, in the multinomial case, we considered two random n random variables, capital X1, capital X2, capital Xn. But that was not a multivariate case because the probabilities were considered individually. X1 has got this value, so the probability is this, like that. Now we are not going to do that. We are going to calculate the joint probability when capital X takes value small x and capital Y takes value small y simultaneously. And if this is the scenario, if this if capital X and capital Y, this pair of random variables has this kind of probability distribution, such a distribution is called bivariate distribution because the number of associated variables is 2. Okay. Now, in case of my previous examples, we always considered, in case of binomial case and Poisson case, we always considered the univariate case because the number of random variable was 1 only. We shall first of all try to solve this particular problem. We will try to understand what is being said over here by the joint probability. What do we mean actually? Okay, so my first of all, the question, you read the question, you note down the question. The question says two caplets are selected at random from a bottle. Two caplets are selected at random from a bottle containing 3 aspirin, 2 sedative, and 4 laxative caplets. What is caplets? Caplets means some kind of oral medicine. Any kind of oral medicine is called caplet. Okay, so there are 3 different kinds of caplets present. One caplet is called aspirin for headache. Sedative is for some kind of sedative, is kind of drug, hallucinatory drug, and laxative caplets means kind of stimulator. Okay, so how many aspirins were there? 3 aspirins were there, 2 sedatives were there, and 4 laxative caplets were there. Now see, if capital X and Y are respectively the numbers of aspirin and sedative caplets. Okay, we have chosen 2 variables here. Capital X is associated with the number of aspirin tablets, and capital Y is associated with the number of sedative tablets. And we are actually choosing 2 caplets at random. Okay, so in that case, we are supposed to find the probability associated with all possible pairs of values of capital X and capital Y. Now, this problem is very important. You just be attentive and try to listen to me carefully. Now, since capital X and capital Y are the 2 variables under question, okay, one variable is associated with the number of aspirin and another variable is associated with the number of sedative caplets. What are the possible values for capital X and capital Y? And we have to keep in mind that we are actually choosing 2 different caplets from the choices. Okay, so you see the first pair 0, 0. It represents it tells you that capital X, number of aspirin, and capital Y being number of sedative caplets. 0, 0 means you have chosen the 2 caplets from your basket, but none of them is aspirin. Neither of them is aspirin nor sedative. Okay, so number of aspirins chosen is 0, and number of sedative caplets chosen is 0. Similarly, in this case, one sedative has been chosen and no aspirin has been chosen. Here, in this particular case, 1 aspirin has been chosen, no sedative has been chosen. Here, 1 aspirin and 1 sedative has been chosen. Here, no aspirin has been chosen, but 2 sedatives has been chosen. And here, 2 aspirins have been chosen, but no sedatives have been chosen. So these are the possibilities. But we are actually choosing 2 tablets, 2 oral capsules, isn't it? Now you see, we are going to find the probability distribution of the given problem. So I have shown you the calculation over here. I have made the chart. In the chart, I have marked all the tablets and their numbers on the topmost row, and I have made 4 columns altogether. The first column is, please mute yourself. It is disturbing. In the first column, I have mentioned all the outcomes, all the possible outcomes pairwise. So I have written 0, 0, 1, 0, 0, 1, etc. Everything is written over here. You see, all the outcomes have been tabulated. 0, 1, 1, 1, 0, 2, 2, 0. All outcomes have been tabulated. We need to find the probability distribution. We need to find the favorable case and the total case. Now, since 2 caplets are chosen out of 9 caplets, why 9? Because if we add these figures, 4 plus 3 plus 2, we get 9. So out of 9 caplets, 2 caplets can be chosen in how many ways? 9C2 ways. 9C2 is 36. So for all possible pairs, my total case is 36 always. So I have kept the third column, value of the third column as same. It has not changed. The total number of cases is 36. Okay, fine. What about the favorable case? Now see how many aspirins are there. 3 aspirins are there, 3, and 2 sedatives are there, and 4 laxatives are there. So for the pair 0, 0, 0, where which actually defines that no aspirin and no sedative has been chosen. This can be, the favorable number of cases will be 3C0, 2C0, and 4C2. Why 4C2? Because two caplets have been chosen. And since the outcome is 0, 0, that means that two caplets are from laxative ones. So from 4 laxative caplets, 2 laxative caplets can be chosen in 4C2 ways. And if you calculate, that will be 6. And corresponding probability will be 1 by 6. Similarly, for 1, 0, one aspirin has been chosen and one laxative has been chosen. But I am interested about the variable, I am interested about the pair 1, 0. Okay, I'm not interested about laxatives. I'm interested about aspirin and sedative. So here I have written it as 1, 0, not 1, 1. Okay, because my random variable capital X represents number of aspirins and capital Y represents number of sedatives. But this choice can be obtained in this, how many possible ways by which this choice can be made, can be obtained. The choice, this can be obtained as 3C1, 1 from aspirin, no sedatives, so 2C0, and 1 laxative, that is 4C1. So the result is 12. And the probability is 12 by 36, that is 1 by 3. And similarly, all the other probabilities have been calculated here. Let me show you one more. So for example, this one, 1, 1. Okay, 1, 1 means laxative has not been considered. Laxative tablets will not be considered here in my chart. Okay, for the calculation, this will come, but we are not interested about laxatives. So here 1, 1 represents, one is aspirin and another is sedative. One aspirin can be chosen from 3 aspirins in 3C1 ways. For each possible way, one another sedative can be chosen from 2 sedatives in 2C1 ways. So the two choices can be made in 3C1 into 2C1 ways by multiplication rule. And for each of these choices, no laxatives will be there. So 0 choice for laxatives, so 4C0. And the outcome is 6. And thus the probability becomes 6 by 36, that is 1 by 6. So we have calculated all the probabilities for all the possible pairs of the random variables capital X, Y. But my probability distribution chart is not complete. I have to prepare the chart properly, because each time we have to keep in mind that we are interested about bivariate distribution. We are not interested about univariate cases. Okay. So here is my chart. The ultimate chart will be written in this particular form. See, on the top we have written the variable x, small x, which are the variables possible cases for capital X, and on the leftmost we have written small y, which are the possible cases for capital Y. Small x has got 3 choices. Small x has got 3 choices. One is the choices are 0, 1, 2, and y has got 3 choices 0, 1, 2. And we have substituted all the probability. We have put all the probabilities here. 1 by 6, 1/3, 1 by 12. 0, 0 has got the probability 1/6. We have put here. 0, 1 has got probability 1/3. We have put here. 0, 2 has got probability 1 by 12. We have put here. 1, 0 has got probability. 1, 0 has got probability 1/3. We have put here. So first of all, you will not see the things in this manner. 0, 0, 0, 1, 0, 2. No, you have to see them from column to row. First, X will come. Okay, now that is up to you. You can put X on the leftmost portion and Y on the topmost portion, but the general convention is to write X on the top and Y on the left. So we will read this in this manner. We will read this as 0 and 0, 0 and 1, 0, 2, like this. Okay, column to row, like this. So all the probabilities which have been calculated in the above table has been put over here. And that is the chart which is in front of you is called my probability distribution chart for the bivariate case. Okay. Now, just like our univariate case, we can also deal with the formula of the probabilities. Since all the probabilities have been calculated, a little thought will yield the following formula for the above problem. So fxy can be written in general as 3cx 2cy 4c2 minus x minus y divided by 9c2. This formula, you put all the values for x and y, possible values for x and y, you will get all the probabilities. Okay. Even if you are unable to find the formula, you don't have to worry about it. If you can show the chart, that will be all right. Okay, our ultimate job is to calculate the probabilities. In any way you can do it. If it is correct, then there is no problem. And one condition has been written here that I have not only tabulated the possible values for x and y, also a condition is there that you have to keep in mind that the sum of these variables x and y must lie between 0 and 2. So what is the formula for joint probability distribution? What is the definition of joint probability distribution? The definition is, if capital X and capital Y are discrete random variables, the function given by fxy is this for each pair of values xy within the range of capital X and capital Y. That means within the range. The range of capital X here is 0, 1, 2, and range of capital Y is 0, 1, 2. So that's why I have written here within the range of capital X and capital Y. This kind of distribution which I have obtained in the above is called a joint probability distribution of x and y. There is a theorem. Now, when we studied probability distribution for univariate case, you try to recall that we talked about two properties of the probability distribution. One property was that all the probabilities must be non-negative. Fx must be greater than or equal to 0. And the sum total of all the probabilities must be equal to 1. Similar will be the case for bivariate distribution. Okay, so in bivariate case, the properties will be represented in the following manner. Now we have got the function of two variables. Okay, this is called the function of two variables. Both x and y are variables here. Yesterday I told you that when I write f of x comma theta, theta is constant. So that is not the function of two variables because theta was constant there. Here, none of these inputs are constant. All of them are variables. So we can consider this as function of two variables. This represents probability, joint probability, and that must be non-negative for each possible pair of values x comma y within the domain, within its possible domain. Okay. And since we are talking about bivariate case, since we are talking about joint probability, so there will not be only one summation, there will be double summation. The double summation fxy must be equal to 1. Okay, the first summation will run over x, possible values of the random variable x, and the second summation will run over the possible values for the random variable y. Fine. Now, here is a problem which I have chosen from the exercise of joint find. Okay, so what is in the previous problem, some conditions were given, the variables were given, definition of the variables were given, and we found the probability in the tabular form. Now what they have asked you to do is that they have given the probabilities in tabular. They have put the joint probability distribution in this tabular form. You are supposed to calculate the probabilities. The problem is the reverse to the previous problem. Okay, hope you are understanding. If you are not understanding, you can anytime unmute yourself and you can ask me. The given problem, you note down in your copy, this given problem is just opposite to the previous problem, which has already been discussed. Now you see, this is my chart. This chart is different from the previous one. Okay, now this is the chart. This is exercise problem number 1 of your exercise. We are supposed to find the joint probability of x equal to 1, y equals to 2. So how can I? Okay, somebody raised his hand. Do you want to ask anything? Sahil or whoever raised his hand. If you want to ask anything, you can unmute and you can stop me at any point of time and you can ask me question. Okay. So we are supposed to find the probability that capital X equals to 1 and y equals to 2. This joint probability has to be calculated from the above table. Now you see, I have calculated probability of that x equals to 1 and y equals to 2 means consider the value of 1 from variable x and consider the variable 2 from variable y and mark this probability, that is 1 by 20. So this probability is 1 by 20. If I write probability of x equal to 0 and the random variable y is lying between 1 and 3, that means you mark 0 over here, you mark 0, and y is running between 1 and 30, 1 included and 3 running between 1 and 3, 1 included and 3 excluded. So these are the two possibilities. You see, these are the two possibilities. For 1 and 2, we have to consider both. What does it mean? It means probability of x equal to 0, y equals to 1, plus probability of x equal to 0, y equals to 2. Y equals to 3 will not be considered because 3 is excluded. So I have written here 1 by 4 plus 1 by 8, which is 3 by 8. Similarly, if you write probability of x plus y less than or equal to 1, what are the possibilities? So possible values of x are 0, 1, 2, 1, 2, 3, and possible values of x are 0, 1, 2, and possible values of y are 0, 1, 2, 3. So this possibility can be obtained in these mutually exclusive ways. X equal to 0, y equal to 0, their sum total is less than 1. Or x equal to 0, y equal to 0, y equals to 1, their sum total is less than 1. Or x equal to 1, y equal to 0, their sum total is less than 1. So they are all mutually exclusive. So I can apply this rule. Probability of mutually exclusive events, union of mutually exclusive event is equal to sum of their individual probabilities. So I have written this as probability of x equal to 0, y equal to 0 plus probability of x equal to 0, y equals to 1 plus probability of x equal to 1, y equals to 0. And all the probabilities have been considered from the table and have been put over here. And the result comes out to be 1 by 2. When I calculate probability of x greater than y, what are the possibilities? First of all, x is equal to 1, y equal to 0 is one possibility. Okay, x equal to 2, y equal to 0 is another possibility. And x equal to 2, y equals to 1 is another possibility. Okay, so these are the possibilities because the possible values for x are 0, 1, 2, remember. We cannot consider the possibility x equal to 0. Fine. So this can be obtained. These choices are mutually exclusive. So similarly, this can be calculated by considering their sum individually, and we have calculated the probability from here. Okay. So thus from the chart we can calculate all the probabilities in this manner. Since time is already running out, let me quickly discuss what do we mean by joint distribution. What is joint distribution function? Just like we did in the univariate case, joint distribution function for bivariate case can be considered in the following manner. It will be represented by the function capital F of x comma y, which is different from small f of x comma y, which will be denoted by probability of x less than or equal to small x comma y less than or equal to small y. Try to recall that in defining joint probability distribution in case of joint distribution, cumulative distribution for univariate case, we mentioned capital F of x, which was probability of capital X less than or equal to small x. Here, capital F of x comma y will be probability of x less than or equal to small x, y less than or equal to small y, which will be defined in a similar way. Double summation, new variables have been introduced, s less than or equal to x, t less than or equal to y, f of st. And x and y will run between minus infinity and plus infinity. This is very complicated. You think that this expression is very complicated, so that thing will be clear to you if I can show this with the help of an example. Okay, so examples always help us to understand the theory. So let us consider my first problem, which we calculated by ourselves, this probability distribution table. Okay, and for this we are going to find the joint distribution. What is it called? Joint distribution function. Okay, so we are going to calculate joint distribution function for this chart. I am going to show you the calculation quickly. I have not finished the calculation. You will finish the rest of the calculations by yourself, and that will be the homework for you today. Okay, so first of all, we need to find the values of the function f, capital F, for all possible pairs. So first pair is 0, 0. By definition, f of 0, 0 is probability of x less than or equal to 0, comma y less than or equal to 0. Now, since it is a discrete case, we can write it as summation s less than or equal to 0, t less than or equal to 0, fst by definition. And since it is a discrete case, only one possible value for s is there. S less than or equal to 0 means s equal to 0. T less than or equal to 0 means t equal to 0. So we get only f00. From chart, it is 1 by 6. When we find capital F of 0, 1, what we do is see carefully. Probability of x less than or equal to 0, y less than or equal to 1 has been written in this manner. Okay. First of all, I will put the variables, I will put the values of the variable t. So we keep this summation s less than or equal to 0 fixed. And inside bracket, I have written f of s0 plus f of s1, because t has got two possible values which are lesser than or equal to 1. One is 0 and another is 1. So f0 plus fs1. Now we shall run the summation on these individual items. So where you see that s is less than or equal to 0. So there is only one case, s equal to 0. So we are putting the values of s equal to 0 over here. So we get f00 plus f01, which is 1 by 6 plus 2 by 9, that is 7 by 18. Similarly, let me show another one. F11 can be written as probability of x less than or equal to 1, y less than or equal to 1. Write this in this manner, and that will be summation s less than or equal to 1. What are the possible values for t? 0 and 1. So we have written it as f of s0 plus f of s1. Now run the summation on individual items. What are the possible values of s? 0 and 1 now. In this case, it was 0 only. Here we have written s less than or equal to 1. So you have to be very careful what is written. So s is less than or equal to 1. So s has got two possibilities, 0 and 1. So we are writing it as f of 00 plus, first of all, we put s equal to 0. So we get f00 plus f01. Then you put s equal to 1. We get f10 and f11. So all the probabilities have been mentioned and have been written from the chart. The values of the probabilities have been considered from the chart, and it is coming out as 8 by 9. So that is how the discrete joint density function can be, joint distribution function can be calculated for the joint probability distribution. Okay. And here is a definition for joint density function. Joint density function is nothing but similar to the joint density function for the discrete case, but here we are considering the variable to be continuous. Okay, just like we did in the univariate case. And double summation will be replaced by double integration, not single integration. And here also joint probability, which is calculated by double integral, should be equal to 1. So I am not going to show you the problems in today's class. We shall be discussing problem on this in the next class, that means tomorrow. Okay, so I'm going to conclude my session today at this point, and by today evening we are going to get the video if it is uploaded and the note in the Google Classroom as well. Okay, so bye for today. I have saved your chat, and I will also send you the absentee list. Okay, so tata, see you tomorrow in our scheduled time.